All right. Hello, students. Good to see you today. I hope you're doing well. I'm still new at this meeting thing, so not promising anything. By the way, sorry about this boring background of the bedroom here. Uh, Zoom has some nice backgrounds, virtual backgrounds they say you can use, but when I try to pull them up and use them, it says because my lighting's so bad, I can't use them. So you're sort of stuck with this. Now I could tilt this back and you'd see the top of the room, the ceiling fan. That's really not much better, is it? Okay. So what I want to do today is to go get you started on the homework on chapter 5. The homework problems are not that hard. It should take you a couple hours to work them. I looked on Wiley Plus, nobody started on them. So I guess my timing is pretty good. But you really need to work them because we are going to have a test on chapters 5 and 6. So when we finish 6, we'll have test number 3. Then the only remaining test will be the final exam. So let's get started here. Let's see if I can share a screen and share this. Okay. Okay. So here's the homework. And like I said, this homework is not hard. Let me move my face down. By the way, if I didn't say it, I hope everybody is safe. All your families are doing well. These are not really hard problems. There are a few gotchas because of the sign convention. It's a little bit unwieldy sometimes. So we'll talk about that a little bit. So here's problem 535. Says the inventor, and I'm not working them out. I'm going to go over real quick, so you might want to have a paper and pencil available. And as always, my numbers are going, what my given information in the problem is going to be a little bit different than yours. But the problem says the inventor has a refrigerator capable of maintaining its freezer compartment at 20 degrees Fahrenheit while operating in a kitchen at 70 degrees Fahrenheit. Uh, Okay, that's usually a freezer you expect to be a little colder than that, but anyway. And claims the device has a coefficient of performance, and there are 3 different values we want to consider, 11, 14, and 12. So evaluate the claims of each of these. So what you do, you just give an information, you have TC is 20 degrees, at the cold temperature, plus 460. Remember, you got to get it in absolute. TH likewise is 70 plus 460 of 530. And just apply the beta max. Beta max is TC over TH minus TC. And when you use temperatures, just use the signs exactly like shown in the equation. So if I solve, now again, on beta max, we use the temperature. These are Carnot temperatures. We do not use the heat transfers. So you have 480, 530 minus 480, that gives you 9.6 as the maximum coefficient of performance of this refrigerator. And so all 3 possibilities that I was given in my problem of 11, 14, and 12, they're all impossible because they claim a performance better than you can get using the Carnot performance. So next one. This inventor claims to have developed a food freezer that at steady state requires a power input, excuse me, of 0.8 kilowatts. Now remember, always power input, all refrigerators and heat pumps and air conditioners have to have a compressor. And that means you have to put power into that compressor. So all of those power inputs are negative, regardless of what the signs tell you. And I'll mention that a little bit later. So he says that you put in 0.8 kilowatts and you can extract heat transfer from the refrigerated area at the rate of 3,000 joules per second. Of course, that is also 3 kilowatts. And and the problem asks you to evaluate this claim for an ambient temperature of 293. So I didn't mention on the other problem, but on these type problems, you ought to always draw this little diagram. I call it a energy flow diagram for these type problems. This is the freezer. I should have labeled these areas. This is the freezer area. This is the outside area. And this is your cycle in this abstract box. You know you're putting in 0.8 kilowatts of electricity, and you know QC is 300 joules per second. That's how much energy you're pulling out of your refrigerated area, going through your system, and then you're going to reject that plus additional energy out to the outside. So again, let's solve for beta max. You got 255. Now these are, they gave you the temperatures in K, so you didn't have to convert them. 255 over 293 minus 255. Now, as you know, these temperatures are always subtracted from each other, so they can be in degrees centigrade if you want to. But you go through and you get a beta max using temperatures now, not heat transfers, of 4.11. Now, what is your that's the best you could possibly get. So what is your actual? Well, your QC, the heat you pulled out of your refrigerated area, is given as 3,000 joules per second, which is actually 3 kilowatts. QH minus QC, which is also equal to Q net. Now, always remember, this Q net is minus, and I didn't stick my minus sign here, I should have. But if you use QH and QC, don't ever add the two to get a big numerical number. It's always the difference of these two, regardless of whether you get a minus or a plus for the difference. Always I'd say absolute difference of them. And you weren't given these, but you know work net is equal to QH minus QC. And that's because, let me see what I can do here. Go down, and I apologize for being so poor on this. In any kind of system, the sum of the heat transfers is always equal to the sum of the work in a cycle. So if my heat transfers are QL and QC, then that's always got to equal to work net. Now the signs are flaky. You have to take the difference between the QL. That's not right. Sorry. It's QH. I'll use a capital H this time. QH plus QC is work net. They go ahead and put the minus sign in there, and they'll say, you know, work net equal QH. It's confusing, I know. I wish it wasn't like that. But remember, when you use this equation, QH minus QL for work net, it's always the difference of these two. Then the best thing to do is look at your sign, make sure it always comes out with a negative sign. Generally, if you use QH and QL with the sense that we always use in that Q into the cycle is plus and Q out of the cycle is negative, you'll come up with the right value of QN, but not always. We'll talk about that later. All right, let's go back to the homework problem. Drop that pen to keep the jiggering. So plug that in, and I get the actual beta. And remember, it's an absolute value, so you don't have a sign just put your absolute signs if it makes you feel better. And you get 3 kilowatts over 0.8 or 3.75. And since this beta actual, ACT, is less than the beta max, then the system is very possible. Next problem. An air conditioner operating a steady state maintain a dwelling at 20 degrees. So what's 20 degrees? 20 times 1.8 is 38 plus 32. That's 70 degrees C. F. A little on the cool side, but okay. Energy is removed by heat transfer from the dwelling at a rate of 32 joules per second, while the air conditioner power is 0.8 kilowatts. It sounds a lot like the other problem, doesn't it? Determine the coefficient of performance of the air conditioner. So again, these are easy problems. Let's draw a little heat flow diagram. I could have been a little neater, could I not? So here's our cycle. Here's the heat we're pulling out of the air-conditioned area. Is this what is this? Air conditioner, yeah, okay. So we're pulling heat out of this area and cooling it, and we're giving this heat off to the outside. And as always, if you pull out this amount of heat, that's QC, 3.22 joules per second, which is 3.2 kilowatts. The amount of heat you got to transfer to the outside is going to be the sum of these, 3.8 and 0.8. All right, let's see if we can get beta actual here. So I'm sorry, what did he say? Determine the actual coefficient. Okay. All right. So QC was given as 3.2 kilowatts. QH minus QC, which is also work net, was given as 0.8. Now, if I use signage, QC is going into our system, so it's positive. We know work has got to be negative, so we'd end up with a minus 4. But coefficient of performance is always absolute, so it's just 4. Now, I believe the problem also asked you to find the maximum. What did it say? Determine the power input required by a reversible refrigeration cycle. Reversible means the best possible case. So what is the beta max? That's also the beta reversible. And again, here we use temperatures. It's an air conditioner, so it's TC over TH minus TC. Refrigerator, TC over TH minus TC. If it's a heat pump, it's TH over TH minus TC. Okay, put in the Kelvin temperatures and I get 29.3. Isn't that see, most of these air conditioning and heat pumps and so forth, they're in real world operation, they're not going to be operating anywhere close to the theoretical maximum. But if we could find a fully reversible one that would operate at the maximum, then it asks you how much power do you have to put in. Well, the beta max is 29.3, and that's equal to QC over WN. Solving for WN, and you get, I left out an equal sign, minus 0.109 kilowatts. Now, when you get this final answer of work, regardless of what signage you come through here with, you assign that negative sign. I want to know that you understand that work input to a compressor is negative. Again, air conditioning, heat pumps, the work is always negative. Okay. All right, let's go to the next one. Like I said, it's hard to make these problems hard. Problem 5047. To maintain a dwelling steadily at 68 degrees Fahrenheit on a day when the outside temperature is 40 degrees. Okay, we got a heat, right? Got a heat here, outside's 40 and we want 68 inside. So we're dealing with a heat pump. Heating must be provided at an average rate of 1200 BTUs per minute. What that means, an average rate of 1200 BTUs per minute, what he's saying there, that's how much heat you have to continuously pump into your dwelling to maintain the temperature of 68 degrees. Or in other words, what he's saying, and the heat loss from your dwelling area is 1200 BTUs per minute. So if you'll put in exactly the amount of heat that you're losing in the form of heat from a heat pump, you'll maintain the temperature. All right. Determine the electrical power required in kilowatts to deliver heat using electrical resistance heating. Now, what we're pointing out here is how much more efficient a heat pump is than electrical resistance heating. B part said a heat, or how much power would you have to put in a heat pump whose coefficient of performance is 3.5? Now 3.5 is absolutely real world. That's typical of a good heat pump nowadays, even higher. And C, a reversible heat pump operating between hot cold reservoirs of 68 and 40 respectively Fahrenheit. That's her gamma max here. And we're going to find out the actual heat pump of 3.5 is going to be well below what the reversible maximum gamma max would be. Okay, the first thing we want to determine the power. Let's see, what was the first thing? Electrical resistance heating. All right, I drew the little diagram, not very neatly again. Here's the area we're heating, so our heat flow is to the area we're heating. And it has to go through this cycle. Remember, that cycle has a compressor, condenser, expansion valve, and evaporator. We'll talk more detail about heat pump and air conditioning cycles themselves later, but it's a whole cycle inside that box. Our beta actual is 3.5. So I went to another sheet of paper here, said solution if electrical resistance heating. Well, in electrical resistance heating, you get 1 watt of heat for every watt of electrical power. So all I have to do here is just convert QH, which is 1200 BTUs per minute, into kilowatts. So 1 kilowatt is 3.413 BTUs per hour. I put the hour on top sometimes instead of putting it right down in here. Maybe if I use this, let me use this point. Okay, in 60 minutes and an hour, and 1 kilowatt is 1,000 watts, and I get 21.1 kilowatts. Now, I didn't have a sign anywhere here, but I know that's power in, and I know if I'm working on a test that Mr. Ezel is going to count off if I don't, 1 point if I don't have my minus sign, so I put the minus sign there. Now, that's how much heat you would have to, that's how much electrical energy it would require to provide 1200 BTUs per minute of heat, which is quite a bit of heat, by the way. So I know right now how much energy would a heat pump require. Well, I know that my gamma actual, and that's not a very good gamma, is equal to 3.5, which is equal to QH this time over work net. Oh, goodness. Lost my screen. I better check, make sure I'm sharing with you the right screen. Okay, I am. All right, so QH now is negative. It's going out of the system here, so it is negative heat transfer. So I put the minus sign in there. I could have put the, I really should have put the minus sign right here, because it is heat going out of the cycle right here. Heat going out into the conditioned space. So if I go through the calculations, minus 1200 minute, now I get to divide by 3.5, my coefficient of performance. So if I go through this same thing, I get minus 6.03 kilowatts. See how much energy the heat pump uses than pure electrical resistance heat. Of course, if I pointed out before, the heat pump has some other disadvantages based on what temperatures you're operating at, whereas electrical resistance heat, it always gives you the 1-for-1 no matter what. So the ratio there, of course, is 3.5. Now, what about a reversible heat pump? All right, with a reversible heat pump, again, we're going to use, since it says reversible, that's the best possible, limited only by the temperatures. So it's TH, not TC, TH over TH minus TC. And I get 18.857. Well, that's certainly about 5 times the 3.5 of a real system. Now we're trying to find the work. So we know that gamma, this is not a very good gamma. Gamma max is equal to QH over QH minus QC is equal to QH over the work net. We know that work net is negative. We can solve for, well, we should come up with a negative answer. And when we do, in this case, we put minus 1200 for the heat, BTUs per minute, divided by 18.857, we get minus 1.112 kilowatt. Of course, that's the theoretically possible. Of course, we got nowhere close to it. Now, next one. Heating system must maintain the interior of a building at 20 degrees C, which we calculated a while ago is 70 degrees F, when the outside temperature is 5 degrees C. 5 degrees C, 1.8 times 5 is 9, plus 32, that's 41 degrees F. Heat pump work fine at 41 degrees F. All right, if the rate of heat transfer from the building through the walls, okay, that's the heat loss in the area you're trying to heat. So as we mentioned before, think about it a second. If you're losing 15 kilowatts of energy out your conditioned space through the walls, ceilings, and which happens, how much heat you got to put in there to maintain the temperature? Well, you got to put in, from your heat pump, you got to put in 15 kilowatts. Now, it's true if you start off with a cold room, say at instead of 20 degrees C, it's 10, and you got to make up 10 degrees, then you'll have to put up a lot more than 15 kilowatts to bring the heat up there. But once you reach steady state, once the amount of heat you putting into that space is equal to the amount of heat going out of it, it'll maintain that temperature forever and ever. So the same situation, the problem wants to know the electrical resistance heating. If a heat pump whose coefficient is 2, that's not a very good heat pump. And then the fully reversible Carnot type heat pump. So in part A, it's just 15 kilowatts. It's already given you the heat loss in watts. So the amount of heat you put in is 15 kilowatts. And QH is heat flowing out of the system, so it's minus 15 kilowatts to get the proper sign. Now, warning, I don't know how Wiley Plus is going to handle your sign. I forgot. I put in all of my signs and I got all the answers right. I don't remember having to change, but if you put in what you think is a right number and Wiley Plus won't take it, then it might be because it needs a minus sign or doesn't need a minus sign. So 15 kilowatts, here's a little diagram. 15 kilowatts going out, you need 15 kilowatts coming in from your heat pump. If you're heating it with resistance heat, then it's 1 watt of heat for 1 watt of electricity. So you need 15 kilowatts of electrical energy. Now let's look if we got a heat pump with a coefficient of, with a gamma of 2. Well, gamma actual is equal to 2. That's equal to Q, oops. That's QH. I'm sorry. That's wrong. That's QH over WN. That's QH over WN. I put the right number in, but wrote the wrong symbol. So if I put QH in now as a minus 15, it should be a minus 15 there. Divided by 2, I get a minus 7.5. Now, even if you don't have the signs right here, I'll give you credit if you realize that at the very end, you got to have a minus sign. I should have been more careful and put a negative sign here, just like I did up there. My mistake. Now, C, what about with a reversible heat pump? Now I switched to temperatures. And that's because I don't want to get off the subject, because if you had a reversible situation, there'd be no irreversibilities due to heat transfer. So that means if you had a 293-degree TH, it would be able to pump in the heat it needs. Let's see, where's TH? TH is on, yeah, with no temperature drop. So that's why you can, in that type of ideal world, your heat transfer is directly proportional to the temperature. In other words, QH is directly proportional to TH. QC is directly proportional to TC. So if you think about it a minute, you can drop the Q's out and have TH times some proportionality constant. If that proportionality constant is true for the numerators, that is the denominator, which it would be, then you would end up with TH over TH minus C, TC, instead of QH or QH minus QC. It's an ideal situation, never really happens. So TH is 293, TH minus TC, I don't really need to convert those. I just look up there and I see it's 20 and 5, 20 minus 5, so I get 19.533 for the gamma max. And then I know gamma max is QH over work net, and I just solve for work net. I know QH is 15 kilowatts, gamma max is 19.533, and I should have the minus sign right here to be consistent. But at the end, I did realize I need to put my minus sign. You guys practice that, putting the right signs in, and let me know how it works out. Maybe I'll go back and modify these to make sure I put in the right signs. In other words, this 15 kilowatts is leaving, going out of the cycle, so it should be negative, going out of the system or out of the cycle. This QC coming in is positive, and the work net going in should come out to be negative. Now, here's a reversible heat pump. That's actually a Carnot cycle. You see it consists of a compression from 1 to 4, an isothermal, that's an adiabatic compression, by the way. Heat transfer is 0, no heat transfer there. Then a isothermal heat is transferred, let's see, how would that, isothermically, the temperature is, TH is constant. Then an expansion down to TC, and TC is constant. We start off at TC, went up to TH, constant TH, down to TC, constant TC. And it says it's a reversible heat pump. P1 is, state 1 is 14.7, P4 is 34.7, V1 is 12.6, that's specific volume, cubic feet per pound mass, and V4 is 7.0 cubic feet per pound mass. The gas is air, obeying the ideal gas law. And okay, the first thing it wants is TH. That's this high temperature. Let's see. So I use this equation for ideal gases. Got two really equations. For some reason, I have trouble remembering them. All right, let's see if my pen's, all right, good. Come on, pen. All right, let's lasso this and get rid of it. Whoops, didn't get it all, did I? Cut. So the two little equations all right, I got to go select a pen. For ideal gas, P big volume is equal to M R T. T is always in degree, is in absolute temperature. That can also apply for a rate equation for PV dot is equal to M dot. And remember, V is V dot, that's volumetric flow rate. That's the same as this book shows as AV. Now the form of the equation we're going to use this time is P specific volume equals RT. We're given this, and this is a constant for air. You just need to look up the right English. So we've got everything. We just need to solve for T. So TH is the high temperature. That's state 4. So we're given 30.4.7. That's P. Specific volume we're given is 7 cubic feet. It's just a messy dimensions as far as it's just plug and chug as far as the calculations. 1 BTU is 778. Now I realize that that sheet we have says 778.3 or something like that. I've been using 778 for 50 years. Too late for me to change. And you won't affect the accuracy this time. You won't get in a situation where I'll subtract a point off because you didn't maintain accuracy. And 144 square inches in a square foot. If you put all that together, now you look this up, that comes from page 86. That's that sheet I gave you with gas constants. So you just look over for air and look over for the English units. So the gas constant for air is 0.6855 BTUs per pound mass degrees R. And if you get everything right, everything will cancel out except the degrees R, and you'll get TH is 655.85 degrees, which around then is 656 degrees R. Now subtract 460 from that. What's that, about 200? That's 196 actually. So the temperature in Fahrenheit is 196 degrees. But again, ideal gases, we use absolute temperatures. And also, this is a English unit problem. As I mentioned on that little write-up, we do not go back and forth from English units to metric units in a problem. Kilowatts sort of applies to both the metric system and the English system. But even in that, in the English system, the heat transfers are generally in BTUs per minute or BTUs per hour or even total BTUs. All right. Now, the same way we find TC. This is, remember, TC is this lower temperature here, and we were given the specific volume at this point. So, and the pressure, so we should be home free. So TC is P1, specific volume 1 over R. R stays the same type of calculation. we get 500.2. Uh-oh, -1. I should have had degrees R. My TC is 500.1 degrees R. All right, I think that's the A part of the problem. I should have step 2. Oh, the coefficient of performance. Oh, it said the actual coefficient of performance. Ooh, I didn't do that right. Did I? Oh, it said it's a reversible. Okay, that got me out. That means it's the best that you can get. So you use absolute temperatures. Only let your gamma max is only limited by the temperature extreme you operate in between. So it's TH over TH minus TC, and that ends up 4.21. Not that great, but you're not operating, you don't have a very big temperature range here. No, actually you do. Let's see. Oh, it's this. This is not, I better not say that. This is not a real world heat pump, this Carnot thing. It's just to illustrate these expressions and relationships. And now here's another one. I didn't like this problem either. It's not real. It's again, this is a Carnot cycle. How can you tell? Because these two cycles at top and bottom here are at constant temperature. That means it's a Carnot cycle. It says the figure shows the schematic of a vapor power plant. We'll start at state 1. We go through a boiler, and this shows, although this line here is not lined up very well, that's got to be saturated vapor. And then we go down at to a quality of 88% right here, going through the turbine. Then we go through the condenser from 2 to 3, and we increase our quality. No, we decrease. We go to more and more liquid to where we only 18% vapor by mass. Then we pump up to a higher pressure. This lower pressure was 20 kilopascals, and the higher pressure is 400. You know, those are not realistic pressures. So that's our cycle. And it wants to know what's the efficiency. Now these numbers are a little flaky, I'll be honest with you. I've heard it said when anybody says I'll be honest with you, you know they're not going to be honest with you. Well, that may be, that's probably true for a used car salesman, but in my case, I am being honest with you. I shouldn't say that. That's a dinky saying. All right, given the schematic of the previous page, we're given that m dot was 100 kilograms per second of water. That's a lot of water. P4 equal P1, that's a higher pressure, 400 kilopascals. That's not a very high pressure. That's only 4 bar. Remember, a bar is 14.5 psi, so 4 to 14, that'd be about 58 psi. That's not a very high pressure. See, P2 is 20 kilopascals. That's well below atmospheric. Whoops. So what I did is I decided to just go through the whole thing, calculate pull all the enthalpies up and calculate all the values of the cycle, the works and the heat transfers and so forth. I looked at the solution to this after I got done. The guy did it real cute. He didn't have to look up but an enthalpy or two, but I think this is more straightforward. But you're asked to find the thermal efficiency of the cycle and that sigma of the cycle. Remember that figure we had, that equation we had was sigma. All right. So I can look up H1 is just H of G, H of gas at 400 kilopascals. I didn't write my page down, did I? That's 2736.8 kilojoules per kilogram. H4, 1, 2, 3, 4. H4, is that right? I'm sorry, I might probably give you a migraine. H4, okay. I'm sorry, H4 is saturated liquid. Absolutely. So H4 is HF at 4 bar, 60474 kilojoules per kilosecond, kilojoules per kilogram. Now I've got to calculate H2 and H3 because H3 and, no, H2 and H3. Okay, that's what I got to calculate, H2 and H3. H4 and H1 I got right off the table, easy lookups. H2, we're given the quality of H2 is 88% or 0.88. So I can calculate H2 from that's the quality equation. H3, same way. I'd given the quality is 18%. So it's HF plus 0.18 times Hg minus HF, which is also H sub Fg, which is calculated for you in the tables. Oh, goodness. I don't know what's, sorry. So, first thing I calculate is Q41. That's the heat transfer in, QH. It's just M dot H1 minus H4. And I make sure I have these proper. What I'm saying is, let's go back to here. Let's get rid of this. Erase it. All right. If we write out our energy equation for a single inlet, single inflow and a single outflow, we would have, draw, we would have, whoops. What am I doing wrong here? I don't want to insert. I don't know why it's selecting that. Don't know. I don't have shapes. Why I'm not getting the pen. I know, because I wasn't doing it right. Okay. Sorry, you can fast forward through this. But remember, for one steady state with one inlet, one outlet, it's, try to make it neater. The M dot times, we're going to go from 1 to 2 now. This is, we're actually going from, it's normally H2 minus H1 is equal Q dot of the control volume minus work, the control volume, work W dot. And for heat, for a boiler, this goes to 0. There's no work done. So we got to go back and look at our figure here. I wish I could bring them up at the same time. Maybe if I bring it way over here. Sorry. So our second H, or outgoing H, is actually H1. So applying this equation to this, we have m dot, the outgoing H from the figure is H1, and the incoming H is H4. And that's equal to the heat transfer. We call it from 4 to 1. So you can see that H1 is a lot higher because it's coming out of the boiler. So you're going to get a plus sign, and that's exactly what you should get. I'll get better about it. So H4 to 1, there we go. M dot H1 minus H4. H1 is a lot bigger than H4 because it's coming out of the boiler. That's going into the boiler. And I got 213,386 kilowatts, which is 214 megawatts. That's a lot of power, Q41. Now let's get the work of the turbine. Now let's go back and look at this again. Look at this equation. Let's draw. In this case, the work of the control volume is the work of the turbine, and the heat transfer is 0 through the turbine. So in this case, let's lasso this and get it out of here. Missed a little, didn't we? Okay, so now we got m dot. Larry. We got m dot. Now that's the outgoing. Now let's see. Oh, we got a negative sign over here. See? So let's solve for work of the turbine. Work of the turbine. This is dot. It's going to equal, put it on the other side, and it's going to equal m dot. See, these are not complicated equations. Put it on the other side, and it's going to be H1 minus H2. And I think that agrees with our subscripts, does it not? Let's see. I think it agrees with our subscripts. Yep. That's through the turbine. 1 is into the turbine, 4 is out. So that's our exact equation for work of the turbine. So what did I get? I got 41,190 kilowatts. Now let's look at the work going out of the work QC, heat transfer QC. Using the same type approach, Q of 2,3, which is, I got QL here, should be QC, is equal to m dot times H3 minus H2, and that's going to be a negative, minus 165,080, and it should be a negative because that's heat coming out of the system. That's heat coming out of here, out of the cycle, I should say. So it's negative. And I also, by the same token, went and calculated the work of the pump. When I got the work of the pump equal to a positive, indicating you're actually using the pump as a little turbine, I knew that was bogus because of the given values of the problem. So I didn't feel like using that work of the pump in the solution. Dang, I'm sorry. So then I went and did it this way. All right, I'm trying to find the thermal efficiency actual. Well, I know it's equal to the work net over QH, but remember, work net is QH minus QC over QH. And that's QH over QH minus QC over QH. So that's 1 minus QC over QH. And I could actually, at this point, I could put in the numbers I got for QC and QH, which I could have done, but now I just subtract or just put the ratio of the expressions for QH and QC and QH. And if you, well, I see I did that, then I actually brought the numbers back. Okay, that's all right. So QH minus QC over QH is, where did I get the 165,000? QC is 165. 165,080 QC. I got to check that. I put it in again right now. That looks a little QH minus QC. Oh, I'm sorry. 1 minus QC over QH right here. 1 minus Q, you probably saw that before I did. 1 minus QC over QH. And although QC is minus and QH is positive, you got to end up with a minus here. You got to be well under 1. This is one of those cases where you have to check your signs, and if they don't, in other words, QC is a negative. So a negative times a negative would be a plus. So you would get 1 plus QC over QH, which you know cannot be right. It has to be a 1 minus. The signs get flaky, I'll agree with you. So it's 1 minus 165,080, which is QC over QH, and you get 22.6% is the thermal efficiency. Not very good. Dang. All right, and the B part said to find sigma of the cycle. Well, this equation looks sort of formidable, but it's really not for a steady state problem. All you do is get the sum of these delta Q's over their temperature. Well, in this case, since it's steady state, it's just Q. So one of the heat transfers is QH, QH over TH. The only other heat transfer is plus QC over TC, and that's equal to the negative sigma. But here's where you got to be really careful. This equation demands that you put in the proper signs for heat transfer. So QH is 213, a plus 213 over 386, we just calculated, over the temperature 416.75. And this next term is QC, but QC is a negative. It's heat transfer out of the cycle. So that's 165,080 over 333, what, 120, oh, 333.2. It's got to have a minus sign here. Got to get that sign right. I wonder if I could do that. Yeah. Oh, okay. I'm sorry. I'm jerking you around. I'll get better. I promise. I should have been using my cursor, just my down key. So if I go through that, I get minus sigma, the cycle is 16.61, or sigma, the cycle, is equal to minus 16.61. And this has to do with entropy, and we'll talk about this a lot later, next chapter. So I've got sigma cycle is less than 0. If I look down here, my three possibilities are sigma cycle equals 0, it's reversible. It's a perfect system, you might say. Donald Trump would call it perfect system. Perfect, gorgeous, beautiful system. If it's greater than 0, that's irreversible. That's the typical. It's what you get every day. If it's less than 0, it's impossible. Well, we got less than 0, so our system's impossible. We violated the second law of thermodynamics. Now, as a check, I decided, well, let's look at what the Carnot efficiency is if I use 1 minus TL over TH. Instead of using this criteria, let's use the Carnot. And if you go through that, you get the Carnot efficiency is 20%, which means no real world, that's the reversible efficiency. Nothing in the real world can beat that. So if I go through and I get a 22.1 for this cycle here, it's bogus. That's why some of the numbers look so flaky, but it's bogus. It's not a real world system. The guy made this up just to test us. So that's the end. I hope you got something out of that, and I hope you worked the homework. I put the due date, I believe, to a week from today. And by the way, we will have a test on chapters, what is it, 5 and 6 a week from the day. And things will get the rest of the course after we get through chapter 6, which I got to do next. After we get through chapter 6 and we've got this chapter 5 and chapter 6 behind us, we're going to get all into real world systems. We're going to look at a power system, a power cycle, a Brayton cycle, an air conditioning, and a heat pump, all real world systems, real world cycles, and that's going to be the rest of the course. And I think you're going to like it. Probably what I'll do on the final, most all the final will be the system work we do. Oh, well, I'll go back and pick up a few. I'm going to pick up that B squared, B1 squared minus B2 squared that some of you couldn't convert. You're going to see that again because I want you to be able to do that. Okay, that's enough. Have a good day. Take care. I'm going to close out now.